Einstein's general relativity perfectly maps the cosmos at its most intense. When monitoring dense neutron stars spiraling toward collision, the orbital decay matches theoretical predictions to extreme precision. The classical geometric paradigm operates under a specific mathematical assumption. It is scale-free. The equations contain no minimum threshold of acceleration where the physical rules suddenly change. At the extreme edges of galaxies, where centripetal accelerations drop to a tiny fraction of a meter per second squared, specifically around 10 to the negative 10, the math stops working. This chart shows the baryonic Tully-Fisher relation. It plots a flat rotation velocity of galaxies against their total baryonic, or visible mass. Across completely different galaxies with varied formation histories, the data plots a perfectly tight line. We have two mathematically sound observations that refuse to overlap: a rigid geometry that works at high accelerations, and a strict low acceleration scaling law that governs entire galaxies. To test which framework holds true, astronomers examine wide binaries. These are pairs of stars separated by tens of thousands of astronomical units, orbiting each other so distantly that their internal acceleration drops into the galactic anomaly range. Standard modified gravity theories operate on a simple conditional rule. If the acceleration between two objects falls below the universal galactic threshold, the gravitational pull should increase, causing the stars to orbit faster than classical physics allows. This data plot from the Gaia DR3 dataset compares physical separation on the x-axis against relative orbital velocity on the y-axis. While modified models predict velocity should curve upward at wide separations, actual Gaia observations lock perfectly onto the descending Newtonian line. The stars are experiencing the exact low accelerations that should trigger modified gravity, yet they behave entirely classically. This creates a severe observational contradiction for standard modified gravity models like MOND. Dynamic vacuum field theory, or DVFT, abandons the idea of a purely geometric spacetime altogether to address this contradiction. The math of DVFT has to demonstrate how gravity can reorganize itself at the galactic scale while leaving the orbits of these isolated, local star systems completely untouched. The baseline assumption of modern astrophysics is that the vacuum is an empty, passive stage where objects move. DVFT removes that stage entirely. Instead, the vacuum operates as a physical medium. Like any physical material, it possesses finite structural coherence and physical stiffness. This is expressed mathematically by a complex order parameter, a single equation that defines the exact physical state of this vacuum medium. The amplitude variable, ρ, measures the local stiffness of the vacuum, its exact capacity to store energy density. The phase variable, theta, acts as a coherence and clock mechanism. Gradients in this phase dictate how physical influence is transported from one point to another. Under this mathematical structure, gravity is not a curving grid. Gravity is the coherent transport of this phase through the medium, weighted strictly by the vacuum's stiffness. Because the vacuum is a physical substance with material limits, it is mathematically required to change its mechanical behavior when pushed beyond its natural capacity. When massive objects force the vacuum into a state of high stress, the medium undergoes Hamiltonian energy minimization, a process where it settles into its lowest possible energy configuration. This high-stress state is called the stiff branch. Standard physics requires gravity to behave as a rank 2 metric field, meaning it operates in multiple dimensions at once. The vacuum order parameter we just introduced is a simple scalar, representing a single numerical value. This equation demonstrates that multidimensional spacetime is actually an emergent property. In the linear response of the stiff branch, it generates an effective response tensor. Vacuum phase rate creates operational clock distortion, while spatial coherence dictates physical ruler distortion. By reacting linearly to stress, this emergent tensor replicates the complex behaviors we observe in dense space, including the bending of starlight and the physical dragging of inertial frames around rotating masses. General relativity remains entirely valid. It is the precise mathematical description of a stiff, highly stressed vacuum reacting to mass. Moving away from dense masses into the deep field, the physical forcing drops below the specific acceleration threshold, known as A0. The vacuum cannot maintain coherent phase over infinite distances. Its maximum coherence length is bound by the Hubble scale, the limit of our expanding universe. Near this boundary, the medium switches to a nonlinear branch to transmit influence. Solving for this equilibrium isolates the modified gravity relationship, yielding the exact velocity-to-mass ratio observed in the baryonic Tully-Fisher relation. Flat rotation curves at galaxy edges occur because the physical vacuum hits its structural coherence limit and reorganizes itself to minimize energy. If the vacuum reorganizes below the A0 threshold, the distant stars measured by Gaia should orbit faster than classical predictions. Older models assume the trigger for modified gravity is solely the internal acceleration between the two stars in the binary system. DVFT requires two conditions for deep field behavior. First, total background forcing must be lower than A0 to prevent phase pinning. Second, tidal share across the system must be weak, otherwise it frustrates the vacuum and prevents coherent phase formation. The wide binaries measured by the Gaia telescope exist right here, deep within the dense local environment of the Milky Way. The Milky Way exerts a massive external background acceleration and intense tidal gradients. This completely overwhelms the delicate internal dynamics of local wide binaries, pinning the surrounding vacuum into a linear Newtonian state. The exact classical orbits measured by Gaia validate the concept of environmental coherence. The vacuum in our stellar neighborhood is simply too stressed to exhibit deep field behavior. A valid physical framework provides strict, testable parameters, rather than retroactively fitting data. To find wide binaries that break classical mechanics, observation must move to the extreme outer halo of the Milky Way, or completely isolated dwarf galaxies. These structures possess the uniquely low external acceleration and incredibly weak tidal shear required for vacuum phase coherence. The theory provides a secondary target for astronomical measurement, the evolution of the deep field threshold across time. Because the structural limit of the vacuum is dictated by the expanding Hubble scale, the exact numerical value of the A0 threshold must scale proportionally with the Hubble parameter as we observe galaxies further back in redshift. Measuring wide binaries in dwarf galaxies and calculating rotation curves at high redshifts offers a strict numerical test to explicitly confirm or destroy this framework. The math demands that we stop treating the vacuum of space as a hollow, invisible grid, and instead recognize it as a physical material governed by structural limits. By modeling these material limits, a single unified set of equations captures both the geometric precision of dense space environments and the massive scaling anomalies found at the edges of galaxies. When we calculate the actual physical capacity of the vacuum, the discrepancy between the solar system and the cosmos entirely resolves.